É um prazer apresentar o professor John Ball. It's my pleasure to introduce Professor John Ball from Oxford University, and he's going to talk to us about compatibility, microgeometry, and materials. Professor John Ball, please.
So thank you very much, and I'm going to describe, I'll put the title and plan over here, you can read it, but I'm going to describe some questions concerning the compatibility of gradients that were motivated by problems of material science. But you'll see that they have very direct connections with fundamental but rather poorly understood problems of the calculus of variations. The questions themselves are really just questions of multidimensional calculus. So let me begin then with the first section there, which is compatibility of gradients. So do we have a pointer? Can you leave that? Okay. Do you have a pointer, a laser pointer or something? So the setting is going to be that I'm going to consider mappings from a bounded domain. How do we do this without? Okay, there we go. A bounded domain omega in Rn with some reasonably smooth boundary, say Lipschitz boundary, and I'm going to be considering mappings from this domain, mappings Y, to a different dimensional space, possibly Rm. So here's the original domain, and here's its image. Here's the mapping Y. And the object of interest is going to be the gradient of this vector field, which I'll write as capital F of x. So this can be identified, of course, with the m by n matrix consisting of the partial derivatives of the components of y with respect to the components of x. So that's a real m by n matrix. This is my notation for real m by n matrices. Now, of course, we have to say what we mean by the gradient, and I'm always going to work in the Sobolev space W1P, W1P from omega to Rm, so P is between 1 and infinity. So let me explain what this is. This is the a Sobolev space consisting of measurable maps Y, whose W1P norm is finite, and the W1P norm, let me see now, I can see it is difficult to do this. Yeah, it slides. Okay, the W1P norm is defined as follows. So it's the more or less the sum of the LP norms of Y and its gradient, or it's equivalent to that if P is less than infinity, and it's more or less the sum of the L infinity norms of Y and its gradient if P is equal to infinity. Now here, of course, dy is interpreted in the sense of distribution. So it's the weak or distributional derivative. That is, it's the derivative such that integration by parts works. So if I take a smooth function with compact support in omega, then this relation expressing the correctness of integration by parts must hold. And the fundamental question of compatibility is to go in the other direction. So suppose we're given a field of matrices f of x which is in LP. When is this the gradient of a mapping Y, which is in W1P? Well, the answer to this question is old and well known. The answer is that the curl of f has to be 0. So that's a necessary condition. The curl of f is 0. So this expresses the equality of the second mixed partial derivatives of y. So both of these expressions are equal to d. If f was the gradient of y and y was smooth, then this would be the second derivative of yi with respect to x alpha and x beta, and this is the same. So this is true in the sense of distributions. Again, so we multiply by a test function phi and do the integration by parts. Right? So this is necessary, and it's also sufficient if omega is simply connected, but not in general if omega is not simply connected. So in some sense that's the answer, and I've called it star. There's another way which I'd like to mention that you might think of handling compatibility, and that is to use the vanishing of the Riemann-Christoffel tensor based on F. So you look at G equals F transposed F, and so an equivalent condition for smooth F is that this Riemann-Christoffel tensor vanishes, expressing the fact you have a flat metric. But unfortunately, I don't know of any way in which you can express the vanishing of the Riemann-Christoffel tensor for maps in W1P. Because you have to, the expression has to be meaningful, and it's not clear how to do it. That would be very interesting to do, exactly because the deformed metric F transposed F arises very naturally in the problems that I'm going to talk about. Okay, now one example of using that formula star there is the Hadamard jump condition, which is going to play a basic role in what I'm going to describe. So suppose I've got a piecewise C1 mapping Y, so its gradient jumps across this surface, which is marked in green. And so here's a point A of the surface where the normal to the surface is capital N. And so because Y is piecewise C1, it's continuous across the surface, the gradient has a limit dy plus at A from above and another limit dy minus of A from below. So we'll call those A and B. They're matrices. Okay, now, if you apply this condition, you find that A minus B has to be a vector C tensor producted with the normal N. So if A is not equal to B, that means that A minus B is a matrix of rank 1, because this is the general form of a matrix of rank 1. And that's the Hadamard jump condition. You can get it formally just by equating the tangential derivatives on either side of the surface. Now in practice, this condition star is difficult to work with in general, particularly when there are constraints on the field F. So let me try and illustrate this by considering such a constraint. So let's take a compact subset of m by n matrices K and ask a sort of the vague question, what can be said about maps Y whose gradient belongs to K almost everywhere? So the simplest thing one might consider, here let me hide the answer because it's interesting, is the case when K just consists of a finite number of matrices, A1 up to AM. Now we just saw over here that if any pair of matrices has a rank 1 difference, then you can put an interface between them. Okay, so let's make that impossible by assuming that the rank of AI minus AJ is bigger than 1 for all I different from J. So you can't put an interface between any two of these gradients. So the question is, can you have a non-trivial mapping just taking these gradients, even though you can't put an interface between two regions where it takes one gradient and the other gradient? So the question is, if dy of x belongs to K almost everywhere, does it in fact imply that dy of x is a constant? Namely, dy of x is AR for some r between 1 and m. And the answer is only been discovered recently, or finalized recently, and it's yes if m is less than or equal to 4. Now, the case m equals 2 was the result of Dick James and myself. That's easy, really. The case 3 is a little tricky, done by Kei-Wei Zhang. The case 4 is difficult, proved recently by Schlebig and Kirchheim. So if you have less than or equal to 4 matrices, you can't have a non-trivial gradient which takes these values of matrices. Remarkably, the answer is no if m is bigger than or equal to 5. And these are amazing examples of Kirchheim and Price. And you can even, if you let m be a bit larger, the last I heard was 12 or something, if you have, say, 12 matrices, you can even arrange it so that the set of points x where each one is taken on is open. Okay? Of course, then you have to add a set of measure 0 to fill up omega. That's really remarkable. You know, you have the gradient equal to a constant on open sets, but there are no interfaces between them. Okay? So, very remarkable examples. So this is, so you can see that even for a finite number of matrices, this is not a trivial issue at all. Well, there's a very simple way in which this kind of question relates to the calculus of variations. Suppose that we have an integrand f, so this is a real valued function. Well, I'll allow it to take the value plus infinity as well, but it's a non-negative function on matrices whose zero set is exactly k. So I've tried to draw it here. So k might consist of some pieces. F is non-negative, and it's 0 on the set k. And let's consider the I of y, which is the integral of f of the gradient of y. Now, of course, if dy of x happens to belong to k almost everywhere, which is the problem we've been considering, then, of course, y is an absolute minimizer of I in a trivial way because it minimizes the integrand. Okay? Can't do better than that. Surprisingly, however, there's some very interesting examples of this situation with non-trivial sets k that occur in elasticity for materials with phase transformations involving a change of shape. Okay? So this is what I'm going to describe next. So these transformations are called Martin-Zittig phase transformations. They are sort of military transformations of atoms with no diffusion, and there's a change of shape of the crystal lattice at a critical temperature, theta critical. So let me describe, first of all, a cubic to tetragonal transformation, which would occur, for example, the alloy nickel 65, aluminum 35, which we'll see pictures of in a moment. Now, this alloy is a cubic crystal for temperatures theta bigger than this critical temperature, theta critical. This form of the material is called austenite. And it is cubic, so this is just one cell. You've got a very large crystal lattice consisting of this cell repeated many times. You have nickel atoms at some points and aluminium atoms at other points. Okay, so now due to energetic reasons, interactions between the atoms and so forth, and the electrons, when you reduce the temperature below this critical temperature, this wants to change shape to a tetragon, which is a brick-like object with two sides equal. Now, I chose the original side length to be 1. Now, two sides are equal to a number eta 1, and the third side different, equal to a number eta 3. Now, everything has cubic symmetry, so if it wants to change into a brick-like object which extends in this x1 direction, equally it will want to extend in the x2 direction and the x3 direction. These will be equally plausible. That's where you get what are called three variants of this low temperature phase, which is called martensite, that are stable for theta less than the critical temperature. And you can describe them mathematically by the three matrices that take you from here to here, three linear transformations. U1 is diagonal eta 3, eta 1, eta 1, and so on. Okay, that's a cubic to tetragonal transformation. Now let me describe something a little bit more complicated, which is a cubic to orthorhombic transformation. This occurs, for example, in the shape memory alloy copper, aluminum, nickel. Okay, now here we see the cubic cell again. It's a little bit more complicated as regards the arrangement of atoms. So this is the austenite that's stable for theta bigger than theta critical. Now a change of shape involves a stretching in one of the cubic directions by a factor eta 3, and then stretchings in two top face diagonal directions by factors eta 1 and eta 2. Okay, now you have three choices for the cubic direction and two equally plausible choices by swapping eta 1 and eta 2. That way you get 6 possible deformed shapes. And so in this case you get 6 variants of martensite that are stable for theta less than theta critical, and they're described by 6 matrices, U1 up to U6, that I won't write down. And then there are other kinds of transformations as well that occur. We'll encounter one of them later. Now, how does one encode this sort of atomistic information into a continuum theory? So we're going to use elasticity theory, nonlinear elasticity theory. So the energy, the elastic energy is, so both dimensions are 3, of course, we live in 3 dimensions. And here's the energy function for the elastic energy corresponding to a deformation y of the crystal at a temperature theta. We get it by integrating over omega, which is a reference configuration for the crystal that we use to label the positions of the particles, a free energy function, phi, that depends on the deformation gradient, dy, and the temperature. This free energy function has to be frame indifferent. It's invariant. The energy doesn't change if you do a rigid rotation of it. That means that phi is invariant to multiplying on the left by rotations r. So r in the rotation group SO3. Okay, now, by adding on a suitable function of theta to phi, you can assume that the minimum of phi over matrices A is 0 for all theta. Okay, so I'll do that. And then it's interesting to look at the set of gradients that give the value 0 to the integrand. So these are the deformations of lowest energy. So let's call that set of matrices K of theta, the A such that phi of A and theta is 0. Now, we try and encode the information on the right-hand screen here into the assumptions on the 0 set K theta. So we're going to assume that for theta bigger than the theta critical, now we're going to use the cubic configuration as the reference configuration, the cubic configuration at theta critical. So now for theta bigger than theta critical, of course we want, well, theta equals theta critical, we want the identity to be a minimizer because we haven't done anything. So therefore by frame indifference, any rotation has to be a minimizer. Okay, so that's why this SO3 is sitting here for theta equals theta critical. Now for theta bigger than theta critical, the lattice will expand a little. So there's a thermal expansion coefficient alpha theta here, which is 1 at theta critical. Now, what about the martensite? Well, we want these to have less energy for theta less than theta critical. So each one of these ui of thetas multiplied on the left by SO3 by frame indifference will be an energy well corresponding to one of these variants of martensite. Of course, these numbers eta 1 and eta 3 and the ones that describe eta 1, eta 2, eta 3 here depend on the temperature again, but they're things you can measure in the laboratory. And so there's an exchange of stability. This is going to be the minimizing set of matrices for theta bigger than theta critical. This is going to be the set of minimizing matrices for theta less than theta critical. And at theta equals theta critical, they're going to have the same energy. Okay? So this is the how we're going to encode that information into the continuum theory. Well, it's a very big subject, the microstructure of materials, so I'm going to try and talk briefly through it in terms of pictures, actual photographs of materials. So first of all, I'm going to start with nickel aluminum, nickel 65, aluminum 35, which undergoes a cubic to tetragonal transformation. So here's the first picture of it, and I want you to notice on the right-hand side the scale. So this distance is 1/1000th of a millimeter. Okay? This is an electron micrograph of this material. It's a single crystal, a perfect crystal, but you see an amazing microstructure consisting of very fine parallel bands here. Now the interpretation of this is the following, that what you're seeing is a piecewise affine deformation of the material in which the gradient alternates between two values A and B in alternate bands. Okay? Now, how does that correspond to what's happening over here? Well, to have an interface, you need a rank 1 connection. So the thing is that there are rank 1 connections between different of these energy wells. In other words, if I take SO3U1 and SO3U2, then there are pairs of matrices on these energy wells that differ by a matrix of rank 1. And they describe the orientation of these interfaces, because the normal occurs as the second vector in the tensor product of the rank 1 connection. So that's how we understand this. So this is a zero energy deformation using two of the tetragonal variants. Okay. Here's a picture in nickel manganese, which also undergoes a cubic to tetragonal phase transformation. This is a high resolution picture. So you see the atoms. Each dot is an atom, or more precisely a column of atoms perpendicular to the screen. And just by looking at it, you see the piecewise affine deformation with your eyes. And now you see that in this case, the bands are even thinner than in the previous one. They alternate between about 6 and 10 atomic spacings. And actually, you can, if you look very carefully, and I try to illustrate on the thing below there, but I don't really have time to explain it. If you look at the atoms, you see that there's one variant on one side of an interface and another variant on the other side of the interface. Here's, going back to nickel 65, aluminum 35, here's another picture, a high-resolution picture, where we see something a little bit more complicated, and I've spent a long time with the person who took this picture, Nick Shrivers, in trying to say something about the details you see here. Now you see a double laminate, or at least you see what we saw before, parallel bands, and then another family of parallel bands that meets it along a strange kind of interface, whose nature is not entirely clear, and there's another one up here. Okay, now to a cubic to orthorhombic. So copper, aluminum, nickel shaped memory alloy. Here's a picture of a microstructure that occurs in this alloy. This is taken below the transformation temperature. All these pictures were taken below the transformation temperature. Now you see again families of bands, but again, interesting interfaces with some kind of tip splitting and things happening here and so on. So this is in copper, aluminum, nickel shaped memory alloy. There are just two variants of the martensite involved here, one which is dark red and one which is orange. Here's a picture with more variants. These are real photographs, okay? They're not computer simulations or artistic things, they're actual photographs. And here you see many more variants involved. And again, this is essentially a piecewise affine deformation of the material. Well, we have here cubic to something transformations. So how does the transformation actually occur? I mean, how does it take place? To start with, it's cubic, and it ends up with one of these microstructures. What route does it take to do that? Well, the thing that you might think would happen would be that there would be a rank 1 connection between the austenite energy well and a martensite energy well. Then you could put an interface between the austenite and the martensite and move that interface across the material, and you start with a little bit of martensite and then you move it across until you've got all martensite. But that way you would see just a single variant of martensite and not a microstructure. And it's a fact that there's no rank 1 connection between SO3 and these energy wells corresponding to the martensite. So we can't do that. So it does something else, which is seen in this picture. Over here is the austenite. So the gradient over here is, say, the identity, all over here. And over here we have one of these laminates again, in which two variants of martensite are used, and it meets the austenite on some funny kind of approximate interface, which is razor flat, you see. Okay. So this is how, in most materials, the austenite changes to the martensite. You get an interface of this type. This interface propagates in this direction, eats up the austenite, and you're left with a single laminate of martensite. So some of the more complicated things I showed occur because different things happen. It's quite a complicated thing that I can't spend too much time on. All right, well, those are photographs, but I thought it might be interesting to actually see one of these alloys. So I've got here a piece of nickel titanium shaped memory alloy. Okay, there it is, it's just a piece of wire, but it's a plastic at the end. Now this undergoes actually a cubic to monoclinic phase transformation, actually 12 variants, not 6 variants. Now I can bend this how I like, and it will stay there. See, it doesn't matter. Now what's happening when I'm bending it is quite hard to believe, but it's true that inside that material there's one of these microstructures. And as I bend it, the microstructure changes, the microgeometry changes, and that's what enables it to bend very easily in certain directions without damaging the material, because it has this microgeometry going on inside. Now, if everything works well, this water here has a temperature above theta critical. If it doesn't, then nothing will happen. Okay? So this is above theta critical. And I hope I don't burn myself. If I do, I'll sue IMPA or something. Okay, there we go. You hear it click? It's back to that. Okay, now you can repeat this many, many times. I'll do it a couple of times. Okay, and you'll hear it click again. Okay. And so what's no, it's not me, it's the materialist then. Don't clap God or something, you know. So why is it doing that? Well, it's above the critical temperature. It has to go back to that cubic configuration. Okay? And that's what's happening. Okay? But it's remarkable in this wire, these microstructures are playing, and this microgeometry is playing this remarkable role. Okay, now, where are we? Okay, so all these pictures suggest a number of questions. Oh, it's wet, is it? Oh, okay, right. So it is. Okay. Okay, good. Now, so it suggests various questions. The most striking question is perhaps why the microstructure is so fine. I mean, we saw fantastically thin interfaces. Well, and part of the solution was in this picture of the austenite-martensite interface that I showed. But you can sort of phrase it as a kind of conjecture that this energy function I theta does not in general attain a minimum subject to given boundary conditions, say where we prescribe the deformation on part of the boundary. If that is the case, then if you take a minimizing sequence of deformation so that the energy is going closer and closer to the infimum, then something funny has got to be happening to the deformation gradients. And the idea is that they oscillate on a finer and finer scale, so that according to this model, this elasticity model, according to the conjecture, this will predict an infinitely fine microstructure. Now, of course, we don't see infinitely fine microstructures, but we see very, very fine microstructures. They're not infinitely fine because this model is not the be-all and end-all of models. There are other contributions to the energy. In particular, the atomic environment of atoms that are on these interfaces is different from atoms which are in the middle of one of the bands. This contributes a tiny amount of energy, but when you have more and more of the interfaces, this tiny amount of energy, football fields of energy in a wire like this, will add up to some kind of energy and stabilize the length scale of the microstructure at a certain size. Well, we'll see later a reason why it's plausible that this conjecture is correct. But to actually prove it is pretty tricky. And as it is, we only know one example, really, which is when we have two variants or three tetragonal variants and very special boundary conditions when we're in the martensite, that is theta less than theta critical. There's one case where one can rigorously prove that the minimum is not attained and that minimizing sequences have to have this kind of oscillatory property. So a second question is, well, can we actually predict what particular pattern of microstructure we'll see? So that's in one sense an existential question. I mean, is it possible to predict it, or would it happen when you repeat the experiment again and again that you will get slightly different microstructures? And if that's the case, then what is it about these microstructures that one can predict? Or what's the sort of... Okay, so this is currently out of reach for various reasons. Well, of course, it's a pattern formation problem. It's really a dynamic problem. I've been talking about a static theory. We don't really know what the right dynamic equations are, but even if we did know what the right dynamic equations are, because there's various different choices, we would, at least from an analytic point of view, have no hope at all at present of trying to understand why we see particular microstructures and not others. However, according to the static theory, you can analyze particular microstructures. And the way it typically goes is you look and see one of these pictures, and you see, well, can I rationalize that according to this energy well picture? And you can do that, and in doing that, you can get some very interesting and useful information, which correspond to measurements and so on. But it's more of a consistency check. It doesn't say why you see one particular microstructure rather than another. It's rationalizing it within the theory, but it's not really predictive. Here's a slightly more sophisticated question motivated by the experiment I showed you. So I could bend this wire in certain ways very, very easily. When I'm doing that, the microstructure is changing inside the material, and it's just using gradients that are sitting at the bottom of the energy wells as a very good approximation. So can we calculate somehow the macroscopic deformation gradients that correspond to these zero energy microstructures? So that turns out to be the same as calculating this set, the so-called quasi-convexification of K of theta. And one way of describing this is that the set of matrices such that if I try and minimize the energy I of theta of y, subject to linear boundary conditions y on the whole boundary equals ax, then for what a is the infimum 0. Okay, so that's one way of characterizing this set. Unfortunately, we don't know how to calculate this for these sets over here, except again if we have just two energy wells. So that does correspond to some phase transformations, but not, for example, to cubic to tetragonal where we have 3. And we'll see later a sort of reason for why we can't calculate these things. Okay. Well, we need some mathematical tool for describing microstructures. And the tool or a tool that turns out to be very useful is that of gradient Young measures, which I'll try and describe now. So let's imagine that we have a sequence of gradients that's bounded in some sense, say bounded in LP for some P. So this could be a minimizing sequence for the energy corresponding to one of these problems. So let me fix J, fix one of these elements of the sequence, fix a point X in omega, and fix a radius delta. Now let's act as a microscopist and examine what's happening in this little ball around X. And what I'm going to do is I'm going to pick a point at random from this ball and look and see what the gradient of dyj of z is. Okay? I pick a point z from here and I look and see what dyj of z is. And I keep doing that. And that way I get a probability distribution on matrices that tells us the chance of seeing a particular value for dyj of z if I pick z uniformly at random from this ball. And this probability measure nu, which depends on x, j, and delta, assigns to a subset of matrices E this value, the n-dimensional measure of the points in the ball where the gradient lies in E divided by the n-dimensional measure of the ball. Okay, now we let j go to infinity, so we're thinking that dyj is oscillating faster and faster with j. This will smear out the oscillations over this ball bx delta, and then we localize by letting delta go to 0. So that should eliminate the dependence on j and delta and give you something that just depends on x, which hopefully will be a probability measure on matrices. Well, that's true. That's a theorem that given any such sequence, there's a subsequence such that this double limit exists. It's a double limit in the sense of weak star convergence of probability measures, but that's not important. And that object is called the gradient Young measure generated by the sequence dyj, or more precisely by the subsequence you've taken. And that was first introduced by L.C. Young and into the PDE literature by Luc Tartar, who emphasized how it could be used in PDE. Here is a simple example of calculating this in the situation that we've already seen occurs in real materials. So let's take a simple laminate in which the gradient alternates between these two values A and B, and the layers will have a normal n. Okay, so we know, of course, that by the Hadamard jump condition, A minus B has to be a vector tensor producted with n. Now let me take the A layers to have a thickness lambda over j, and the B layers to have a thickness 1 minus lambda over j, where lambda is between 0 and 1. And now I let j go to infinity. This, of course, then becomes an infinitely fine laminate. And what's the gradient Young measure corresponding to this? Well, it's clear that you've got a limiting probability lambda of seeing the value A for the gradient, 1 minus lambda for seeing the value B, and 0 for seeing any other value of the gradient. And therefore, the Young measure in this case is independent of x and equals lambda a direct mass at A plus 1 minus lambda a direct mass at B. Now I would like to do something a little bit more complicated and, well, not very much more complicated, but the calculations are complicated and I'm not going to show those to you. And go back to this issue of the austenite-martensite interface. You see this picture again. And how do we describe this in terms of gradient Young measures? So, well, over here we have just the identity. We have a probability of 1 of seeing the identity. So there the Young measure should be a direct mass at the identity. Now over here we've got one of these laminates, right? So over here nu x has got to be lambda direct mass at A plus 1 minus lambda direct mass at B. And now we want A and B to belong to these martensite energy wells. Okay, so A belongs to SO3UI, B belongs to SO3UJ. So when can you find a gradient Young measure which has this form? Well, it turns out that the answer is that it's if and only if the macroscopic deformation gradient here, which is the average, lambda A plus 1 minus lambda B, is compatible with the identity across this plane which has normal M. And that relationship is here, that the identity minus lambda A plus 1 minus lambda B is C tensor M. Okay? Now you know where all these energy wells are, so you can try and solve the problem of when you can do this. And in other words, what are the possible A's and B's and lambdas and C's and M's? It's a very nasty calculation, though elementary, because it just involves, matrices. And it leads to one of the most famous and useful theories of material science, which is called the crystallographic theory of martensite. And it enables you to calculate all the orientations of these habit planes between austenite and martensite. For example, in a cubic to tetragonal transformation, there are 24 such habit plane normals, and you can say something about the relative thicknesses of the variants and so on and so forth. Okay, so it's a very successful theory. Now, more about Young measures. There are two important properties of them which I want to mention. First, that the Young measure carries the information on weak limits of any continuous function of dyj. So, if you've got a continuous function on matrices, and I look at f of dyj, then what is its weak limit? What's its limit in the sense of averages? Well, so its weak limit is equal to the expectation of f under the Young measure nu x, which is given by this integral, whenever that weak limit exists. Okay? So it carries exactly the information about all weak limits of f of dyj. The second point, which is very intuitive, is that suppose that K is a closed subset of matrices, then dyj tends to K in the sense of measure. That means if I put any open neighborhood around K, then the Lebesgue measure of the set of points where dyj is outside that neighborhood tends to 0 as j goes to infinity, if and only if the support of the Young measure is included in K almost everywhere. So the support tells you the limiting values that are taken by the sequence. Now, what is the question about compatibility phrased in terms of Young measures? It is this. When is a family of probability measures on matrices, depending measurably on x, the gradient Young measure of a sequence dyj? That's the obvious analog to the question about compatibility of gradients. And it has a remarkable answer. There's a question, which was found by Kindelera and Pedregal. The answer is if and only if three things occur, two of which are not so interesting for us. The first is some kind of growth condition that says something about the original sequence being bounded in LP. Forget about that. The second is that the center of mass of the Young measure, which is actually the weak limit of dyj, has to be a gradient. That's obviously a necessary condition, and that's one of these three conditions. What I want to concentrate is on the third condition. The third condition says that Jensen's inequality, that the expectation of f under the Young measure is bigger or equal to f of the center of mass of the Young measure, has to hold for almost every x for every quasi-convex f, satisfying some growth condition, if p is finite. So what is this mysterious thing, quasi-convexity? So here's the definition. It was introduced by Mori in 1952. So a function f is, an integrand f is quasi-convex if Jensen's inequality holds for gradients satisfying linear boundary conditions. So the integral of f of dv is bigger or equal to integral of f of a for any v, which is, say, c1, which on the boundary is equal to ax. So, of course, the gradient of the boundary data is equal to a. So it's saying that if v is equal to ax is linear on the boundary, then that linear map it gives you a minimizer of the integral. And, of course, the integral on the right-hand side is just the measure of omega multiplied by f of a. So that's the definition of quasi-convexity. And, well, one could give a lecture course in quasi-convexity, but I don't have time to do that. But what is known is that this condition, quasi-convexity, is the central convexity condition of the calculus of variations. So here's a picture to try and describe quickly what is known about it. So first of all, if f is convex, so there are various convexity conditions, and this slide is to tell you the relationships between them. So f is convex implies f is polyconvex. What does that mean? Polyconvexity means that you can write f as a convex function of the list of all minors of the matrix A. That's 1 by 1 minors, which are elements of A, 2 by 2 minors are 2 by 2 subdeterminants, and so on, right up to the maximal thing. That's polyconvexity. Polyconvexity implies quasi-convexity. In fact, it's the only sort of easy way of verifying quasi-convexity. And quasi-convexity implies rank 1 convexity. Rank 1 convexity says that the function is convex in direction of matrices of rank 1, and we've already seen why matrices of rank 1 are important. Now, the converse implications are in general false if both of the dimensions are bigger than 1. If one of the dimensions is equal to 1, then all these things are the same, and convexity is the central condition. But when both of the dimensions are bigger than 1, the calculus of variations is a completely different subject, because quasi-convexity plays the central role instead of convexity. The most important counterexample was found by Schwerak, which says that rank 1 convexity does not imply quasi-convexity if m is bigger or equal to 3 and n is bigger or equal to 2. Now, quasi-convexity is essentially necessary and sufficient, this is lying, but essentially it's necessary and sufficient for the existence of minimizers. Now look at rank 1 convexity. Rank 1 convexity is convexity in the direction of a matrix of rank 1. But now these Martinsitic energy wells had rank 1 connections. So if you look in the direction of a matrix of rank 1, you see that gives one of these rank 1 connections. You see it's 0, the function is 0 where it hits the energy wells, and it's positive elsewhere. No such function can be convex. Therefore, none of these functions that describe crystals are rank 1 convex, and therefore they're not quasi-convex either. But I said that lying quasi-convexity was necessary and sufficient for the existence of minimizers. So that's what makes us believe that you don't get minimizers in general for these problems related to crystals. Now, the problem about quasi-convexity is that nobody knows how to check whether it's true or not. It plays the central role, but no tractable characterization of quasi-convexity is known, and it is known that for these dimensions, m bigger equal to 3 and n bigger equal to 2, there is no local characterization. You cannot give me a set of inequalities on f and its first 10 billion derivatives that are necessary and sufficient for it to be quasi-convex. Right, so we've seen that it's more appropriate to ask questions about young measures for these microstructure problems than about exact gradients. So in other words, so now I'm onto another section, compatible and incompatible sets of gradients. So it's more appropriate if we've got this compact set of matrices. Instead of the original question we asked was, what can we say about maps y satisfying dy of x belonging to k almost everywhere? Instead, to explore the question, what can be said about gradient young measures nu x satisfying that their support is contained in k almost everywhere. This is a better question from the point of view of problems of microstructure. Now, I want to explore this because we saw that the kinds of sets that arose in these theories of materials are of the form a union of some other compact sets. So I want to consider the case when K is a union of other compact disjoint sets. And I'm going to make a definition that these disjoint compact sets are incompatible if, whenever you have a gradient Young measure that's contained in the union almost everywhere, in fact, it must be contained in just one of the sets. So that means that you cannot mix at the level of these sequences of gradients that are in more than one of the sets. Okay? Otherwise, we say that the sets are compatible. So let's take the case that we took before, where Ki consists of a single matrix, Ai, where again we assume that there are no rank 1 connections. Here there's a difference in one matrix in the example, in the result we had previously. Namely, the Ki are incompatible if n is less than or equal to 3, but it's false if n is bigger or equal to 4. The difference was with 5 matrices in the exact case, but it's 4 matrices in the approximate case. So the case of 3 matrices is a deep theorem called the 3-matrix theorem of Spirac, and this is an example of Tartar, but it's equivalent to one that was found by Scheffer in his thesis. Okay, so I try and want to prove something, so let me prove the case n equals 2, because it's very instructive and quick. So what we have to, we can suppose, so we've got 2 matrices now, and the rank of their difference is bigger than 1. So we can assume one of them 0, and the other, which we'll call A, has rank bigger than 1. Okay? And so what have we got to do? We've got to take a Young measure that's supported on these 2 matrices. So this is the only Young measure that's supported on, the only probability measure that's supported on 0 and A. It's a convex combination, 1 minus lambda x direct mass at 0 plus lambda x direct mass at A. Okay? And we have to show that actually it's either a Dirac mass at 0 or a Dirac mass at A. That's what we've got to do. Okay, now, A has rank bigger than 1. That means that there is some 2 by 2 minor, J, that is not 0, because if all 2 by 2 minors are 0, the matrix is of rank 1. I'm going to apply Jensen's inequality for the quasi-convex function J. In fact, for minors, the quasi-convexity inequality is an equality because minors are quasi-affine. They satisfy the Jensen's inequality with equality. Okay, this is related to it's a statement of the weak continuity of Jacobians, which was proved by Reshetniak. So I'm going to write down that the expectation of J under nu x is equal to J of the center of mass of nu x, and see what happens. Very interesting. So over here, of course, we get 1 minus lambda x j of 0 is 0, plus lambda x j of A. Over here, we get j of, now the center of mass of this is 1 minus lambda x times 0, which is 0, plus lambda x times A. So I get the lambda x j of A is j of lambda x A. But j is quadratic. So this is lambda squared x times j of A, and j of A is non-zero. So lambda x is equal to lambda squared of x almost everywhere. So lambda of x is either 0 or 1 almost everywhere. But then you easily complete it. If lambda of x is 0 or 1 almost everywhere, then the center of mass, which is a gradient, has to be 0 or A everywhere. But A has rank bigger than 1, and I said that for 2 gradients, that implied that this center of mass was either 0 or 1, or A, and that actually implies that this is either a direct mass at 0 or direct mass at A. So you see that this information connected with quasi-convexity is of crucial importance here, and it's a simple result, but not completely trivial. Here's a more complicated example for a cubic tetragonal transformation. Let's take K1 to be SO3, that's the austenite energy well, and K2 to be all the martensite energy wells. So here's a result that so we have these numbers A to 1 and A to 3, so I'm going to arrange them in order. So and I'll write them as eta 1, eta 2, eta 3. So now, of course, eta 2 is equal to eta 1, but that enables us to define the least one, eta min, the middle one, eta mid, and the biggest one, eta max. And so if these conditions are satisfied, then in fact K1 and K2 are compatible. So actually that's a slightly weaker condition on the lattice parameters eta 1 and eta 3 that allows you to construct an austenite-martensite interface. In fact, in the eta 1, eta 3 plane, and here eta 2 is equal to eta 3 because it's a different notation here. So the union of these darker regions is the set of points where you can prove that the austenite and the martensite are compatible. This lighter shaded region is the one where you can make one of the interfaces that I showed before with a simple laminate. So this suggests an experiment that you take a material whose eta 1 and eta 3 lie in the darker region but not in the lighter region, and the theory should predict that you'll see a different way of austenite transforming to martensite than the one that's normally seen. And I keep asking material scientists, or trying to find somebody who knows how to do this, to find a material which has the lattice parameters there and to do the experiment. Now there's a general theory about, well, there's some general statements you can make about incompatible and compatible sets of matrices that are interesting. So first is, if you have, say, two incompatible sets of matrices, there's a transition layer estimate, which goes like this. So you have to have some condition on the domain omega, satisfies a cone condition, and some p, you're given some p, and then there's some constants, epsilon 0 and gamma 0, such if epsilon is less than epsilon 0 and y is a W1P map, then you have this estimate. So what does this estimate say, and what are the things in it? Well, we've got various sets here. So omega 1, so n epsilon of ki is an epsilon neighborhood of the set of matrices ki. Omega 1 epsilon is the set of points where you're within, where the gradient is within the epsilon neighborhood of k1, and same for omega 2 epsilon. And then the t epsilon, that's the transition region, that's a set of points where the gradients are elsewhere, outside these epsilon neighborhoods of k1 and k2. Now, the assumption is that k1 and k2 are incompatible. So that means you should not be able to mix the gradients in k1 with the gradients in k2. And so that's what this says. It says that the minimum of the measures of omega 1 and omega 2 times some constant is bounded above by the integral over the transition region of 1 plus dy to the p. So that's telling you that you have to have a transition region. Either the volume of it has to be big, or the gradients inside it have to be big. And it's an interesting corollary of this estimate. Incidentally, this estimate is proved using a kind of covering lemma technique, which I don't have time to describe. So one corollary of this is that if you have incompatible sets of matrices, then epsilon neighborhoods are incompatible for epsilon sufficiently small. This is some non-trivial piece of information, actually. This is another application, actually the one that motivated it, which is kind of interesting. Suppose I take two matrices A and B with no rank 1 connection between them, so they're incompatible. And I consider a W that has a local minimum at A and a slightly lower one at B. Then this estimate tells you that the gradient, that the mapping whose gradient is A, the higher one, is a local minimizer of the integral in L1. So the idea is that you can't lower the energy by introducing a little region where the gradient is near B, because there's then a transition region where you have higher energy. And so this is related to hysteresis in certain experiments involving phase transformations. Now, there's a connection with quasi-regular maps. Let me remind you what a quasi-regular map is. So a map, now we're considering maps from omega in Rn to the same dimensional space Rn. And a quasi-regular map is one whose the nth power of the gradient is less than a constant times the determinant of the gradient of y. Now, if you look at that inequality, you see there are two ways that you can solve it, either by taking dy of x equal to 0 or by taking dy of x not equal to 0, right? Now, there are deep theorems of the subject which tell you that you can't mix these two alternatives, i.e. that if y is not constant, so dy of x is not 0, then in fact dy of x has a positive determinant, strictly positive, almost everywhere. Now, using this and the same technique that proved the transition layer estimate, you can prove a sort of young measure version of that. So if you have a set K of matrices with a determinant of a strictly positive, a compact set, then 0 and K are incompatible. You cannot mix 0 with this set K. And this gives, for example, a new proof of Sverrek's three-matrix theorem, which is, he gave two deep proofs. It's not an easy thing to prove. You have to use something deep. In this case, we're using this deep result from quasi-regular maps. So his theorem said that if you have three matrices with no rank 1 connections, then the sets consisting of those three matrices are incompatible. And it follows immediately from what I just said, because there's a reduction to the case of two by two matrices, and where one matrix is 0 and the other two have positive determinant. So you just take K equals A2, A3, and so the theorem tells you that 0 and K are incompatible, so you either have to be a Dirac mass at 0 or you have to be in this set, and then the two matrix theorem tells you that that would imply that you had a Dirac mass at A2 or A3. There's another quasi-regular proof of Stala and Farocco of this result too. Well, I don't think I have time to complete what I was going to say about the generalizing the Hadamard jump condition. So maybe I just show you something about the pictures. So the idea of this is to generalize the Hadamard jump condition so that it applies to an arbitrary Lipschitz map and an arbitrary point and an arbitrary normal. So the idea is that the question is, can we define what we mean by dy plus of A and dy minus of A in such a situation? Well, it's pretty clear that since this thing's Lipschitz and the derivative could be oscillating furiously as you'd approach A, then these things, if you're going to define them, are going to be sets rather than individual matrices. And so it turns out that you can define these sets. I won't say exactly how it's done, but it's done using blowing up in a little ball around this and using Young measures. And you can define them, and then you get two theorems which generalize the Hadamard jump condition. And the first one says that there is a matrix of the form C tensor n in the difference of the convex hulls of these two sets. And then the second theorem, which uses information on quasi-regular maps from the theory that I described, that if both dimensions are 2, then the same is true where you replace the convex hull by the polyconvex hull, which is something defined in terms of these minors of the matrix. Anyway, it's a smaller set and therefore a kind of better result. And it's known that this result is not true if the dimensions are bigger than 3 and n bigger equal to 2. So why would one be interested in doing things like that? Well, that's because some pictures that you see in material science are more complicated than the ones that I've showed you before. So here is a nice one. This is copper, aluminum, nickel. So you can imagine now this has got 6 variants of Martensite, which are all in this picture. So this is kind of more or less 6 gradients arranged in some way that's very difficult to see. But you see here kind of fractal or self-similar like behavior as you approach some interface. So it's kind of interesting in order that you can calculate possibilities like that, to be able to take, say, a point here on this interface and say how the gradient on this side is related to the gradients that we find over here, because that can tell you, for example, things about orientations of interfaces and so on. So that's the kind of motivation for the theory, but I mean we're a very long way from understanding this kind of picture. So I stop there.
Thank you very much. John Ball was a very enlightening talk. We have time for a few questions. Yes. So.
Can you give a couple of key references for your subject?
Okay, I think Yeah, perhaps the easiest way to get into the subject is that there's some lecture notes of Stefan Müller, which you can download from his website at the Max. Stefan Müller, M-U-L-L-E-R. So he's one of the directors of the Max Planck Institute in Leipzig for mathematics and the sciences. So if you go to this website, you find that, I mean, you can buy the book too, but it's easier to download it from the website. So these were written maybe 3 or 4 years ago and give you a kind of overview of the sort of things I've been describing.
Can you comment on the problem you mentioned about the connection with the Riemann-Christopher tensor?
Yeah, so I mean, it's a question of whether you can write the Riemann-Christopher tensor in sort of a divergence form, with sufficiently many integration by parts so that it's meaningful for Sobolev mappings, and I don't know how to do that. See, that would be very useful in these kinds of problems because it's exactly one of these energy wells, SO3U, is exactly corresponds to having F transposed F equals U squared. So that gives a single value for the metric actually. So that's why it would be so useful, but doesn't seem to be possible. But I'm not a differential geometer, but
I have a question about, is it possible to frame this problem of finding the convex sets in terms of free boundary problems? Or is it useful?
Well, it's not, I'm sure it's possible to do it. Of course, in some sense here we're using the Lagrangian or material picture, so that in some sense the free boundaries are defined by the mapping. But in this kind of problem, I've not seen that done, phrased like that in some way that's been useful. But I mean, it would clearly be possible to do it. But.
Well, if there are no further questions, let's thank. Oh, I'm sorry, there is a further question. Elena, please.
In your part 2 of your talk, what you discussed, number of results for theta less than theta critical.
Yes.
That were valid for n equals 2, actually true for n equals 2.
Yes.
I was wondering what's special about it.
Okay, so what's special about n equals 2, and it may be special for n equals 3 as well, is that so now I told you that polyconvexity implies quasi-convexity, but the converse is not true. Now, gradient-Young measures are characterized by quasi-convexity, which we don't understand. So now if you want to, so what you're trying to do in these problems is to calculate quasi-convexification. So that means so a set of matrices is quasi-convex if it's the zero set of a non-negative quasi-convex function. Right? So now, in principle, then to calculate a quasi-convexification, you'd need to understand quasi-convex functions, which you don't. Now, it turns out that when you have 2 energy wells, you can get away just with using the information from the minors. Okay. Now, for 3 energy wells, in the cubic to tetragonal case, we don't know whether it's just a bookkeeping matter and that the minors will give the correct answer, or whether it's a fundamental issue and that you need other quasi-convex functions. In fact, there's a kind of sort of sub-mystery to me that even for 2 wells, you don't seem to have the right to have had the luck that one has had. In other words, I don't know at a deeper level why minors work in this case when in principle they shouldn't, you shouldn't be able to get away with that. So it may be, I have a feeling that minors have a greater significance than, for some reason that we don't understand than they should have. But, so that's the reason anyway.
Well, thank you very much, Professor John.